talking about some recent geometry-related research at Waymo and some of the various directions that we have done explorations in and get some results. What is Waymo? We are Alphabet self-driving company. We like saying we're building the world's most experienced driver, and we're focusing on two categories: moving people, which we do through Waymo One, our driving service, and Waymo Via, which is our goods moving service. And this includes, like, trucks, big trucks like this, and also local delivery. Waymo has been already driving in public roads for over 10 years. And over these 10 years, we have done over 12 million self-driving miles on public roads, over 15 billion miles in simulation, and across more than 25 cities in the US. Google, the self-driving project started at Google when it acquired a moonshot led by Sebastian Thrun that had competed, a group of people that competed in what was known as DARPA Grand Challenges in the 2000s. Sebastian's Stanford team won that challenge in 2005 and placed second later in the second challenge. And so when we started, the goal was to drive, there was a challenge, and the goal was to drive 10 100-mile routes, quite iconic routes close to San Francisco. In the Prius vehicles, and the bar was set high, so you had to drive each segment completely without any human intervention. And so remarkably, within about a year, they succeeded. And so here's some interesting examples from the segments that early Waymo project drove. And these are, if you are from California and San Francisco, you will recognize a lot of these. This is particular iconic drive, the most curvy street in the world. So some of these demos were done, I mean, even though they were done 10 years ago, they would look good for, most self-driving company demos even today. And so then the goal was, okay, so the team proved to themselves that, hey, we can, our technology, this is a promising area to have a product, and it's worth pursuing, and then set about finding a best way to commercialize the technology. And so Waymo invited some Google employees to start testing our self-driving technology on highways. And what we found was quite concerning. So these are some clips of Waymo employees. Typically, they could get, Google employees could get, test this service when driving to work and commuting and so on. And you can see people here, doing things they really should not be doing, like texting and looking at your computer and charging and putting on makeup. And probably the most concerning one of all is the next one. This person is asleep. And so what pushed us over the line was this final video, the driver, that's not an acceptable behavior. And so there was a clear over-reliance on assistance technology once it gets to a certain bar of quality. And that's a valuable insight. And we believe nothing short of full self-driving would really do as these technologies become mature. So the goal was to focus on full self-driving. And then in 2015, we brought this new vehicle to public roads. It's called Firefly. So it's a prototype vehicle designed from the ground up without any pedals or steering wheel that could drive without them. And it tests what a self-driving vehicle could truly be like. And so, yeah, later that year, we completed the world's fully self-driving.
Okay, take care.
The person in this vehicle is Steve Mann. He was by himself in that vehicle. He's a blind person who invented the project, and he was kind of the first real full self-driving passenger. This is footage from 2015, driving in this Firefly. Navigating the streets of Austin. See, there's
I've never been in Austin, Texas. Now I'm driving in Austin, Texas.
So in 2017, we began our next phase where we put a fleet of driverless cars on public road in Phoenix. And we've been testing vehicles in driverless mode, in fully driverless mode in public in some amount ever since. In 2018, we launched Waymo One, the world's first commercial self-driving service. And last year, we started ramping up our fully driverless rides, where no human is in the vehicle, for members of our early rider program. And so before COVID-19, we were serving 1,000 to 2,000 Waymo One rides per week, and about 5 to 10% of them were fully autonomous. And so this is an example of our more modern
driving by itself. There's no driver, Daddy. See?
That is nuts.
It's pretty crazy. It's like there's a ghost at the steering wheel.
I kind of feel like royalty being paraded around in this thing.
School zone.
Look at these guys. Looking over.
Are they?
No driver.
Go!
What?
This little Waymo thing is cruising.
Oh, it's a pretty sharp turn. We made it pretty smoothly.
Thank you. Do I say thank you?
We're here. We made it, and I didn't have to drive.
So, I don't know, I find this type of driverless experience really inspiring. We're working to bring this type of experience closer to more people in the near future. Let me show a couple of the maneuvers that you have to navigate when doing fully self-driverless in Phoenix. This is an example of an unprotected left turn. Here at this intersection, it's regulated by traffic lights. In some cases, this is an unprotected intersection. You need to see the vehicles really far away and be able to accurately predict when you can safely cross, right? And you need to do this maneuver with really, really high, without failure, right? And so that's an example where we make the maneuver. Here's another example I will show you where actually we're still doing a left turn and someone runs the red light as we're doing it. So you have to be prepared for.
That's awesome. You see that? That car ran the red, and then our arrow turned green, and it waited for that car to pass.
Oh wow. That's perfect.
Exactly what's
Awesome.
Right, and so in addition to cars, we also kicked off a trucking program that started in 2017, and these are Class 8, the big trucks. We started adapting our technologies to this platform and testing on public roads in California, Arizona, and Georgia. And most recently, we partnered with UPS and shipped some parcels from the Metro Phoenix store to Tempe hub, right? And so this is an example of trucking. So this is a truck executing a lane change maneuver on the highway. For a truck, those are rather challenging because it's really big and it needs to often potentially create space for itself to pass. Okay, so some videos and sharing with you this self-driverless evolution of Waymo. And now let's go a little more and talk about autonomous driving and the challenges there, right? And so at a high level, it is a problem of mapping sensor inputs. So at Waymo, we have LiDAR, cameras, and radar, which see around the vehicle all in 360 degrees and up to, several hundred meters away. And then you map from this sensor input, you're supposed to understand the world and ultimately output controls that drive the vehicle. This is steering and acceleration, right? So this is the problem of mapping sensor input to actions in the world. So maybe, we live in the age of deep networks, so maybe we should do this with a deep network, right? Is that a good idea? People have tried, right? And there is actually a seminal work. Alvin, it was a seminal system that could, 30 years ago, more actually, it could drive on roads doing lane following, trained end-to-end with a neural network. And recently, as deep neural networks became popular, there was more focus on, hey, can we solve this as an end-to-end approach, just train from inputs to controls? And it's really appealing if you can do it, because then it's a matter of collecting a lot of data and training your vehicle to execute and mimic what human drivers would do. Right now, the issue is that such approaches, people are still working on them, but so far they have not been able to match the quality of production self-driving systems that are being developed by the leading companies. And so I'll talk a bit more about how companies like Waymo Stack looks like and what lessons there could be and what are exciting directions of research as a consequence. So first, let's see what makes the problem difficult of self-driving, and it can help potentially contrast it against another area where AI has been extremely successful already, which is, say, the game of Go, where work by DeepMind, AlphaGo, and AlphaZero set standard for superhuman Go performance, outcompeting even the best players in the recent years based on reinforcement learning advances. And so in the game of Go, it's a beautiful game with a really simple game definition. It's a deterministic game where you just, you follow move by move. Now the space is, I would say, in some level complex, because at each move you have close to 400 positions you can put a stone. And so it results over the length of the game in an extremely large search space and possible set of configurations of the board. Now in self-driving, it's a bit of a different setup. So we have really complex input. We have millions of pixels coming from cameras and scans from lidars and radars. And we have a stochastic environment populated by human actors, pedestrians, drivers, potentially animals, and other agents that are quite unpredictable and non-deterministic that we need to deal with, and the actions of which we need to be able to anticipate to a good extent to safely navigate the environment. And we have quite a simple output. So, we're moving on a 2D manifold. We just need a 2D control trajectory. And we just need to execute that safely and get us closer to the route or the goal that we're interested in, right? So it's quite a problem of a different nature. And here's some of the illustrating some of the difficulties, especially in the input, right? So we have a huge diversity in the environment. So you have different weather, times of day, and different seasons that cause very significant variance in the sensor inputs, probably the most so in camera, but also in lidar and radar. We're navigating very complex environments. The environments have a lot of rich semantic context. So for example, here you have the traffic light states, you have rules of way at the intersection, you have things like pedestrian crossings, and people's behavior is quite strongly determined by the semantic context. And now you can see also the behavior can be complicated. People try to cut you off. When you're driving conservatively, drivers start cutting you off. Right now it's green, but the pedestrian is somewhat blocking us. Now we need to navigate the second crowd of pedestrians and know when it is safe to complete our maneuver. So for those that live in cities like SF, where I live, I know exactly where this intersection is. Right here we are successfully making the progress, but this is part of a routine set of problems that you need to solve if you have to drive in these environments, right? And so you need to be able to model and anticipate and predict behavior in complex scenes. And last but not least, there is, of course, a long tail of events. Here's a kitty running in front of us. Some events happen once in 100,000 miles. Others happen in millions and more. And so we need to build a system that is robust to a diverse set of things that can happen in the environment. And there is indeed a very diverse set. I'm not going to talk about them in much more detail, but here's one example, and I'm happy to report the kitty escaped unscathed. The passengers, the driver, everything was good in this situation, right? And these are ones that we need to handle. And last but not least, so in games like Go, where you can play do reinforcement learning and lose millions of games and play against yourself and as a result improve, this is not so easy in our case, at least when you do it in the real world. You need safe operation. and cannot do collisions for the benefit of learning. You need to ensure safe operation at all times, and that imposes some difficulty and constraints on what you can do. Right. So how do companies solve this? All right. Currently, modern autonomous driving stacks have a modular design. And so it consists of standard building blocks, such as perception, BP, and planner modules. And as data flows through these modules, typically there are several trends that are consistent across most stacks. And they're actually quite intuitive and good to pay attention to, right? So first thing that happens is you go from pixels and scans. That's the initial input. Typically around there, after perception and in behavior prediction planning, you're mostly doing reasoning on objects, relationship, and trajectories, which are extracted from the initial sensor input, right? And it's a lot more concise and potentially generalizable representation about interactions that we need to model. So that's one trend that happens. And the second trend I would highlight is that you're moving from perspective view, perspective projection, camera images, right? Or range images in LiDAR, they're also images. And so from that representation, typically there is a mapping that happens to top-down view, Euclidean space. And so most relationships and geometric interactions later in behavior prediction and planner often are modeled in this Euclidean top-down space, as we call it, and actually results in significant improvements in generalization than purely operating in a perspective representation. And that's been consistent, at least in the models recently in papers that we have seen, right? And so that's one type of processing that happens in the system and trends. Another one is that, planning also can be hierarchical. And so this is an additional hierarchical structure to encode and handle both long and short-term decisions. So the router plans a high-level route that the vehicle wants to execute. And the planner makes decisions to pick what are good trajectories to execute on that route. And then the controller makes sure that the trajectory is executed on a low level, right? And that's typically structure of most planners used, right? Now, when you think of having such a system, of course, now, how do you put machine learning in the system? The team we have, research team at Waymo, is primarily a machine learning team. And so we're trying to improve and generalize the system using machine learning. And, so now what type of learning applies? Earlier in the stack, in perception and behavior prediction, or parts of behavior prediction, supervised learning is really, really popular. This is where say the objects and their relationships and the structure and the environment is being extracted. In recent years, self-supervised learning has become very popular, and later in the talk, I will give you some examples of some of the work we do in this domain. Right, and in planning, you need to execute actions in the environment, and the actions actually do affect the environment. And so what that means is that you potentially cannot just do supervised learning. You need to evaluate the behaviors your system over in closed loop, as they call it, over longer rollouts in the context of other environments, like in simulation, right? And so in this context, other types of learning become relevant too. So cost function learning, imitation learning, and reinforcement learning. And we're exploring some of those, right? So that's a modular system, right? And it's been key to getting good performance in our domain because it's designed to capture these key intuitions and structure from our environment. It's built into the module design. And so in other words, if you're a machine learning person, you would say we've put inductive bias in this model, right? And it allows also an engineering team to make parallel progress on the various modules, which speeds up development towards milestones. But one known, and it's been also true in other domains, it's a known drawback with pure modular development is that, so engineers do choose what is the interface between modules. And so that in those interfaces pass only signals chosen by the engineers. And those may not be all the signals that are relevant, neither are they often optimized such that these are the signals that best improve the modules downstream, right? So this is I mean, it's a engineering choice, and often evaluated on its own merits, right? And so also, as each module is evolved separately, which is a benefit in one way, but in another way, it limits, unless you tie the evaluation across modules, and which is actually quite challenging, then each module does not improve the ones downstream, right? And so one potential exciting direction of research in ML is to build neural network, which remain modular in nature, and they produce intermediate outputs that we understand, that are structured, and potentially can be added as losses in the network. And they also, but this network also in their design would encode the intuitions and structure from our domain, right? And so this is reasoning about objects, interaction, building out those abstractions. And so in addition to those, of course, you can also propagate signals and embeddings through the network. So you're not purely limited to the interfaces you create. And so these networks can, in theory, be trained on multiple tasks across the stack simultaneously and still be guided about various intuitions about the domain and have additional supervision and so on, right? And so later in the talk, I'll tell you some recent research work that we did with Waymo that's along these directions, right? But first, I will talk about a data set that we made to support the investigations of such topics by the academic community. And you know, these topics can include such end-to-end modeling investigations, but also much more. And I'll give you a more diverse set of examples after I present the data set. So this data set that we created, we call it the Waymo Open Data Set, and we started work on this soon after I joined Waymo in the summer of 2018, right? And so I will describe you what we so far have released, and also I'll give you an update on the latest developments. Next, so what makes a good data set for our domain? It should have multiple sensors, right? Similar to the ones that are currently popular and being used. Those should be high resolution, synchronized well to facilitate research. Then you want a large data set with many objects and labels. I think past data sets such as Kitty, while they're excellent data sets, are quite small. And so then they don't address the operating points that we really see in when we actually building the meaningful models. And a lot of the work then can reduce to fighting overfitting, which is really not exactly the problem that we actually see when we work on self-driving currently. Also, you want diverse data sets. Ultimately, a lot of the challenges in self-driving is to have a system that can handle a really wide set of situations and generalize to new ones well. And it should be temporal. I mean, the nature of our problem is very temporal. We see video, or range image video, you may call it, of the world, and time is a huge part of our setup, and leveraging it is important. And of course, we want high quality labels. So you're dealing with self-driving. It's an important domain where you want high standards for your labeling, especially in such released data sets. And so not all data sets are created equal, which we did our best to provide a data set that really covers the points above. So what is in this data set? Oops, let me see if I can click. First, the sensors. We chose to release a data set with camera and LiDAR. At Waymo vehicle, the camera is at the top, in the middle of the dome, the majority of the cameras, and you have a mid-range LiDAR associated with it. They're really well collocated, so you can get as close to good RGBD input than any current self-driving data set out there. Then you have 4 near-range LiDARs, ensuring you have really good visibility for objects near ourselves on all sides, and you have some radar as well. In the current data set, we have not released. We've chosen not to release radar. And so as of today, there is almost 2,000 20-second scenes captured at 10 Hertz by LiDAR and camera. And the sensors are synchronized. We release calibration, vehicle poses, exposure times, and so on. Over 11 million 2D image labels in 1,000 segments, and over 12 million 3D LiDAR labels in 1,200 segments we have released. Right. and you can see here's the 5 cameras. They cover more than 180 degrees at the front of the vehicle. And we chose this at some consideration of size of data set and maximum utility for the things that we release. So when you compare to data sets from the time that we created ours, Kitty has been extremely influential. It's been there from the early 2010s. Some of you may be familiar with it. It became the standard for publications and has really helped evolve the state of 3D perception and computer vision for autonomous driving applications. But there's a key limitation to it. It's really small, right? And it's potentially more than order of magnitude too small. And we've seen this, and it adds significant, it can distort results, especially, right? So now models and representations that are really good at data augmentation and learning from low data regime do best. And that's not exactly always the same models that do well in the large data regimes. And so we wanted a data set where you can try all regimes, right? And in ours, you can see that there's a lot more frames. There's 390,000 LiDAR spins, right? All annotated. And there is 5 cameras associated with each of those, images associated with each of those spins. So it's a very large data set. The range is up to 75 meters. We truncated it. That's not the maximum range of our LiDAR. Yeah, and we have 64 channels in the LiDAR. And yeah, you can see that at least, how should I say, we up to 75 meters, the data set has really good resolution in all directions with camera and LiDAR to do research, and it's diverse. So we captured different environments, different conditions, time of days, and some interesting scenes like construction. And in those, we labeled pedestrians, vehicles, motorcycles, cyclists, and signs. That's what we have labeled so far. And so we keep improving the data set. Initially, we released data from 3 cities, San Francisco, Phoenix, and Mountain View. And in March, we released data from rainy Kirkland, Washington. And that was partly inspired by a domain adaptation challenge that we added, where we have a problem setting where you're trying to generalize from data in sunny locations and San Francisco, Phoenix, and Mountain View to this different rainy location in Kirkland with somewhat minimal labeled ground truth and a good number of unlabeled scenes, right? And so this is one of the challenges we had. Here's an example of the data in the format we released. This is LiDAR, released as range images. We have the first return, which is range intensity and elongation in the signal. Elongation is a new type of signal that we have at Waymo. For lack of time, I will not go into detail. You can check the documentation. And then for certain range scans, we have a second return. And those are given to you as well. And this is an example of a labeled point cloud with all the vehicles, pedestrians, and signs, and so on in an urban scene. You can see that there's fairly significant complex scenes that we have in the data set. This is an example from downtown San Francisco with large crowds of pedestrians and vehicles crossing intersection. We also released 2D camera labels, so they're chosen to be tightly fitting boxes. So they cover only the visible part of the vehicle and sense the frustum that contains all the points from a specific vehicle. And this complement the 3D LiDAR boxes. LiDAR boxes are the guess of the full extent of a vehicle or a pedestrian. And so also this is one of the largest data sets for 2D detection and tracking research. And hopefully this could be of interest to the computer vision community as well. And of course, for these 2D boxes, you can associate the 3D boxes corresponding to the same vehicles. So you have all the information you want to do interesting modeling. And so this is an example of a scene that we have modeled, another scene. This is in San Francisco somewhere, right? And you can see there's a lot of boxes of different sizes and aspect ratios, and in multiple cameras, all 5. Now, the Waymo dome, right, synchronizes the camera and LiDAR really well. The LiDAR is a spinning LiDAR, so it moves at 10 hertz and makes a circle. And as it passes through the center of a specific camera, then the camera itself has a rolling shutter that coincides in direction with the LiDAR spinning. And maximum care is done such that, especially in the middle of each camera, the timings really align, so you can get really good correspondence between RGB of the camera and the LiDAR scans. And that's one of the advantages of our data set. And we also provide a rolling shutter model in our release earlier this year as code. And that allows you to correct for artifacts that occur due to high speed. So what happens is that still the alignment between camera and LiDAR spinning is not perfect. And each pixels in camera are captured at different time as the vehicle is moving. And the same is true for the LiDAR points. And so to correspond them, you need to do you cannot use the standard pinhole projection, you need to use a more sophisticated model, but it really makes a difference. So because our vehicles move really fast, so they can, in 1 second, they can move, many meters. And so now the rolling shutter time may be small, but even for that time, the vehicle has no trivial displacement. And you can see it in areas like this pole or this pole in the back. If you just use the standard projection model, the alignment is poor. But if you use ours, then you get really nice correspondence and boundaries. So with this data set, what we did is we launched 5 challenges in mid-March and invited people to compete on tasks like 2D detection tracking, 3D detection and tracking, domain adaptation, which is the Kirkland scenario. Here's some examples of images. And of course, there's LiDAR, associated LiDAR in Kirkland. And we organized the workshop, Scalability in Autonomous Driving in this year's CVPR, where the winners of these challenges presented their solutions. And you can go check them out online. There's presentations by all of them, along with the video of their presentations. There is write-ups on the winning solutions, and you can see what models worked well. Our leaderboards remain open to new submissions, so people can always check their models on our problems and against the state of the art there. And we had a very robust set of challengers, right? 165 teams participated from academia and industry, right? And over 100 unique entries on leaderboards. And so that was really gratifying to see. We didn't know going into it how popular it would be, but it ended up quite popular, and some really interesting solutions and techniques were tried. So now let's go and talk about Waymo research. And first I will present a couple of works that are along this modular but end-to-end type of models that I alluded to earlier in the talk. And so one work that we had accepted at this year's CVPR is called STINET, and it's a model that was aimed to do simultaneously 3 tasks: detection, tracking, and prediction of pedestrian motion, right? And so how did this model work? So you start with, it's a LiDAR-based model primarily. So you start with LiDAR scans from several different time steps, and you process each and compute backbone features from each scan. Now you take these features across several scans, and you do region proposal network. And what we do may be a bit differently than typical, even though I'm not sure we're the only ones, there might be others. For each anchor in this RPN, we propose simultaneously several bounding boxes, one for each position of the object corresponding to the anchor in the timeframes in the input frames, right? And so that gives you a tube, a space-time tube of where the object was. And so you do this for all objects, right? And you pull all the high-scoring anchors with high confidence. And now this additional structure allows you to extract some interesting features. And so what are these features, right? So one type can be the local appearance features. So you know where this pedestrian was, say, in several timeframes. And you can take the embedding from these timeframes corresponding to these locations, so potentially even process the point cloud corresponding to the position. And so that can give you features across time. These are the local appearance features. What does your point cloud what do you look like at the time, right, at each time frame. You can do something called global appearance feature, which is if you take the bounding box of where the object was across time, and you look at the embeddings in that whole area, right, that gives you a good idea of how the object was moving, in addition to some other appearance cues. You can get embeddings from that. And finally, you can just encode the trajectory itself because we have the corresponding anchor boxes, and you can process that and make a feature out of the trajectory for the pedestrian as well. And so you can extract all these features and append them to the temporal proposals features. And now when you have this enriched feature set, now because especially during prediction time, you can have these features and objects directly model their interactions. So you can do this with a graphical neural network where various pedestrians and objects in the environment can do message passing to each other and adjust their behavior prediction posterior, right? And so that's a model that captures all these tasks in somewhat natural way and being trainable end to end, right? And so what are some of the lessons from this model? So let's just understand what we're comparing. So the metric here is a bird's eye view, so top-down average precision for detection. Point pillars is a standard model from around 2018, which just processes a single spin from the environment, single lidar spin. And multi-view fusion is an upgrade of point pillars, actually Waymo published a year ago. If you're interested, you can see we're taking an interesting way of combining processing in both perspective view and then top-down view in a lidar detection model. So IntentNet is a baseline by Uber where they stack several frames without computing some of these more sophisticated features at the end. And actually for pedestrians, stacking several frames is a really powerful baseline. It gets you a lot of gains compared to a single spin. And this is our STNet. So this additional structure gives you somewhat limited detection gains, at least according to the detection metrics, which are pretty lax, right? So if you have an IUU of 0.5, only so much gains you get from this sophisticated feature in that case. But on more high accuracy tasks like prediction, and especially for the more challenging cases where you have fast moving objects, the gains actually become quite significant, right? And so let me parse this table for you. So this is a task of trajectory prediction in the Waymo open data set. So this is where is your pedestrian going to be in 3 seconds. And you're supposed to guess, and now you compute, L to error in centimeters. And this is average L to error, and you can see that the faster a pedestrian is moving, the more this additional structure is actually helping, compared to a model that's simply stacking frames. And that's really interesting to see, right? So this kind of is some evidence towards the high-level directions that I was talking about earlier, where modular and end-to-end together may be interesting. And now what about the map, right? So we talked about agents and having a model that captures their interactions. Those interactions do not happen quite in a vacuum. They happen in structured environment that we reasonably well understand, right? So when we drive, we often have a map. This map can be either created offline, right, and uploaded to the vehicle, but also can be created in an online fashion as you go, right? Perception, part of the challenges in perception is to reconstruct parts of the map that are relevant for driving, because every map cannot have, complete fidelity. The environments change as you go. Most aspects of it can change, and you need to be able to perceive and understand that and adjust your model, right? And so typically most perception models use the map as some kind of additional sensor. So you feed the map as an input to your detectors and trackers potentially. And typically, at least until recently, most approaches would feed the map, render it as an image, and then apply convolutional neural network to the image and extract some map-related features that then participate in whatever task you're executing, perception task. Now, the issue with doing this is first, The map information is relatively sparse and it's also very rich. So there's a lot of channels, there's a lot of different semantics that need to be represented. And so you end up with I would say that the range in which you need to understand your mapping domain is quite large. And so you end up with something that's very costly in compute and memory because you have a sparse map at long ranges that you encode densely with many channels. Furthermore, also in many cases, you have fairly accurate estimate of the features of the map that can be continuous. And here, when you render it in an image, you can end up with quantization artifacts. And last but not least, so convolutional neural nets, especially because they apply small kernels, filters, they're not that great at modeling long-term structures. So for example, understanding, hey, these two lanes later on merge in 100 meters, so I need to execute certain maneuver or predict. That's not very amenable to modeling well with the networks that we have, right? Because you need many layers until you have visibility at such long distances with the standard kernels that we use, right? And so our approach is, hey, why don't we just process the map in its original native vectorized form? And so it leads us to polylines, right? So if the map is made of polylines, right, let's model everything as polylines. So what are some examples? You can have, say, stop sign can be a point, a crosswalk can be a polygon, you have lanes and past agent trajectories and so on. Those can be modeled as just a straight up polyline, right? And now we can split, so each polyline can be processed independently and get an embedding for it. And now we have, then we can process polyline subgraph that corresponds to specific primitive and get features for those, right? So you have the first level, it's a hierarchical processing where at the first level you process polylines or groups of polylines. And then at the second level, you now have a global interaction graph that does message passing or joint information exchange across all of these different types of polylines that make up your map in the environment. And this type of model is implemented as self-attention. So it's a transformer layer, right? And it is trained with, first of all, L1 loss for the trajectory prediction of the object that you're interested in. But we also added a map completion loss that also seems to help, which is you can mask out certain road graph features. And you can ask this node to the model to predict them in the context of the full environment otherwise. And so that seemed to improve our model as well. And so when compared to state-of-the-art models based on rendering map to an image and applying convolutional neural net, in this case ResNet 18, we get significantly better performance for a fraction of the parameters in compute, right? So that's very promising. And so one of the benchmarks on behavior prediction is this Argoverse data set. And at the time when we were writing the paper, the final version, we compared the error at 3 seconds. And also this is the average error. And at the time we were best in that metric on the leaderboard, and actually really active space of research behavior prediction currently. And the state of the art has moved significantly in the recent months. They actually had a workshop on this at CVPR as well on the latest winners of this Argoverse challenge. And in parallel, of course, at Waymo, our state-of-the-art models have improved dramatically, and I look forward to sharing with you more recent work that we have on these topics in future conferences, right? But one thing, again, to summarize, this is an interesting instance of a more end-to-end type of model with more structured outputs and potential benefits you can get from trying to model some of the structure and the environment there. One, I would guess, aside is it also, so now you can see that modeling maps as polylines and vectors and not just as potentially pixels is interesting and can even improve prediction. And so there is now an interesting question of, can we learn to reconstruct such representations? It's kind of a dynamic road graph reconstruction as you go, and how good can you make it? And how does that tie into prediction? So these are some very interesting challenges. Now our data set for now does not have associated maps, but it's something we're considering and looking at providing. So far, I showed you some results with detecting and tracking objects. And you can say, okay, so this data set is for detection and tracking, but actually it enables a lot of interesting other applications. And I'll show you a couple of those that are not just purely detection and tracking. And one of them is a deep structure from motion framework that we have been working on at Waymo jointly with collaborators from Google Brain. That's Ariel Gordon and Anilia Anguelov, who have themselves done a lot of really great work in video-based self-supervision. And so this VIRA framework is a framework covering scene geometry, semantics, and dynamics. And I will show you some of the results we have with it and some potential future applications. So what is a deep SFM structure from motion framework? You guys know that structure from motion learns 3D geometry from image sequences by exploiting motion parallax. And a deep framework typically warps images in time and applies per pixel losses, typically photometric loss, as supervision signals. And by doing this, you can train your depth and potentially flow and even motion models further. So that's been a really popular area, right? So there's a good amount of work there. Here is, for those that are not that familiar with this direction, I'll give you an overview. So you have two images from a video, and you can train a depth prediction, per pixel depth prediction model that gives depth for every pixel. And in our setting, you can really co-train this with LiDAR, which is available in the open data set, which dramatically improves the quality of the predictions. What you also can do, right, is you can train ego motion models. So you learn to predict the transform between the two images. And for moving objects, you may want to also learn to predict the residual flow, how they're moving across time from this pair, right? And so now you have a very detailed understanding of the world. And given this, now you can take your first image at time t, and using the depth estimates for this image and post-transform and residual flow, you can now render a new image that takes those into account, right? So that's now your estimate based on pixels from image from time t. What does an image from time t plus 1 would look like, right? So now, if that's your predicted appearance at time t plus 1, of course, you can compare to the actual image over here and see and push losses based on photometric consistency and potentially other consistency losses. And that's been quite powerful. Now, these losses now can help train your models, the depth, the blue boxes, depth estimator, and so on, right? And so this idea has given some very interesting results. And so for us, some characteristic of our work is, first, in the open data set, our vehicle moves fast, and modeling rolling shutter is quite critical. And so we paid significant attention at doing this really well. So there's the library I talked about that we released that demonstrates how to do it. Also, our data set has the camera shutter timing, so you can really do this properly, right? And this is important, as I showed. You can avoid significant incorrect displacements between LiDAR and camera at high speeds, and also across potentially reprojections from multiple cameras. Another thing we did is, so we tried to predict depth in multiple cameras simultaneously in the same model, and we see significant gains from doing this. So given these, say, 5 videos with 5 cameras that we have in our data set, training on all of them, we saw significant improvement, up to at least 6% in the depth metrics than training on a single view alone. So that was really interesting. And then last but not least, right, in the Waymo open data set, we have many hundreds of thousands of spins with associated camera. I think compared to data sets like Kitty, that's a whole order of magnitude larger and allows you to train much better models of this deep SFM type of models. And you know, inside at Waymo, we have yet orders of magnitude more data, so we can train even better models with that. But from our data set, you get non-trivial amount already, which is exciting. And so here is the differentiable view synthesis I talked about. So given our models, You can just move the viewpoint in the scene and get yourself these types of renderings, right, from a single frame. These are from a single frame. So, now what can you do with this? Overall, right, first, you can train yourself really good models for depth, motion, and dynamics. And you can also use VIDAR as a consistency modeling framework, right? So if you have models that predict certain kind of semantic output on the image, can be segmentation, object detection, flow estimation, and so on, right? You can actually push gradient through these models based on labeled data using a correspondences given to you by the VIDAR framework. And these consistencies can, be beyond the photometric consistency. They can be in the semantic type of losses, in semantic consistency. And I'll show you more examples later on, right? But this is an exciting overall framework that can be used for many things. So some results. So this is examples of the depth from single camera image that we can obtain, having trained our model on data like the open data set. This is in 5 cameras. You can see that, the boundaries, depth boundaries are quite crisp. The depth is meaningful. Here's a few more qualitative results. What's exciting is areas, for example, with very strong shadows. The depth is still predicted very accurately. Areas where there's raindrops on the camera, here you can still make out, the model can still make out that there is a tree behind the raindrop well. And this is areas with heavy rain and relatively dark, and it captures the depth of vehicles well. So that's really nice. Another thing you can do is this is in supervised learning of 3D flow. So this is color coded. So orange is moving to the left, green is moving to the right. This was learned by our models without any special flow supervision. This is just an emergence of applying the VIDAR framework. Please ignore the bounding boxes in red. They were not used to train anything. They're just detection boxes shown just as context, right? Another thing, so a little more on how to use this as a consistent modeling framework. So you have some labeled data on which you can train a semantic model, perception model, predicting, say, panoptic segmentation, instance segmentation, object detection, and other potential tasks. I mean, you can say lane detection and so on. And so what you can do with VIDAR is you can take an image that's unlabeled from a video stream, right? And you can predict the semantics of this image given the model. And using VIDAR, you can now synthesize what the semantics should be at another frame, T+1 of interest. And now you can compare the transferred semantics from frame T to the actual predicted semantics at this frame, and you can push a loss for this, right? And that's really interesting. That's a separate loss that is independent of the standard losses that you can. And now you're putting your unlabeled data to use. And so there's a preliminary results on this type of work that are online by a paper by Anelia's team, on which we're also co-authors. And so this is an example of improving semantic segmentation in COCO by leveraging Cityscapes dataset, which is a semantic segmentation dataset in autonomous driving, which is very different domain. And still, when you apply VIDAR type of constraint and losses, consistency losses for segmentation over time, results on MS COCO improve significantly. So that's exciting. And now we're looking at applying the similar ideas to a lot of models in our stack. So this much about deep SFM. One other interesting domain I wanted to talk about is simulation, and specifically sensor realism in simulation, right? So if you remember from that diagram I drew, for planning, we need to test the model in an environment over a significant period of time and check whether the behavior and the outcomes are acceptable. And that often can be done in simulated environments, right? Now, the more the models become end-to-end, the more you want to do this scenario replay in the simulator with realistic sensors in the loop, right? And so now there's a question, how do we get realistic sensors in novel environment settings that are variants on ones you've captured before? So here is an example. in the initial scenario that was of some interest, our vehicle drove the green path and gave us certain sensor data from that about the scene. And now in simulation, our planner decided to drive the dotted path, right? And now we want still realistic simulation. It would be great if we could still somehow produce the sensor input from this new path and potentially for novel positions of other agents in the scene that may be reacting to us, right? So what may be a good data-driven way to do this? Traditional solution in autonomous driving has been to generate synthetic data on top of a gaming engine such as Unreal, which requires significant manual effort because now you need artists and you need assets and place them in an environment, and the assets have material properties, and you need ultimately to model the various properties of sensor generation in a physics-based way, given those material properties. And with 3 sensors especially, that's not quite as trivial. And also, what's interesting is that still a significant domain gap can exist because this physics-based modeling doesn't always approximate best how your sensors actually see the environment. And so there is this question, hey, and that's also the core of our idea, is like, hey, can you reconstruct the environment in vehicles using our own sensors to the best of our ability? And then from some type of representation that we reconstructed, now we can render novel vehicle and scene configurations during replay and to the best of our ability, given that representation, and then fix any resulting issues using machine learning, so with a GAN model, right? And so that is a high-level overview of what we did. So in a little more detail, you guys all know what a circle is, right? So you have this disk in 3D space that groups of them can approximate arbitrary 3D surface shapes. The issue that we see typically is that there's a trade-off. So you want the circle to be somewhat large so that you have stable geometry estimation. But if it's large, and potentially if you give it a single RGB associated with a single color, right? Now you have this trade-off. Well, you want somewhat large surface for stability, but then you lose resolution. And so in our paper, we chose to texture the circle with from multiple RGB pixels. So you have a grid of camera-derived texture samples. And we also store a codebook of textures per circle based on distance. And that is because often there's, in simulation, you can come to certain objects from much closer or much further away, and it's easier it's a better model if you have separate texturing for those cases. And so when you have this reconstruction, right, so this is an example, it's a real image on the left, and in the middle is baseline circles where you have a single color for each circle. And this is our texture enhanced circle that you can see that it looks quite good already, right? Now, it doesn't always look perfectly good because you have artifacts. So for example, as you render the new environment, there may be parts of it that you just occluded. They can be artifacts in the circle reconstruction. There is effects such as, also reflection and so on. And so you want to ideally have a machine learned model try to improve those artifacts. And so for this, we have image synthesis with a GAN network. The synthesis is it takes our best possible reconstruction from a 3D representation. And then it tries from it to produce what a real image in that situation was like, right? And so we have paired data where for images that we already captured, we can render our circle reconstruction and force a model to produce the image. And we also have a lot more of unpaired data where we can either just take other images captured by a vehicle for which we may not have good reconstruction in circle land, or we can render novel views from our circle reconstruction that do not correspond to any images at all, right? So such images were not even seen, right? And so we have a cycle GAN that can leverage both this paired and unpaired data. And this is a high-level diagram of it, right? So you have a supervised term that you can apply to this paired data. right? So you can say, hey, I want from this 3D reconstruction to create the actual image that you see. And then you have adversarial and cycle consistency terms that you can apply to both paired and unpaired data. So this means that ultimately we want the images to look realistic, the reconstruction images compared to images that we see. And we also want, we actually have a backward cycle that makes, that tries to reconstruct our surfal representation and the semantics associated with it from images as well. And so we can apply all these losses. And so when you do this, right, you can do some interesting things. So here is an example of a scene. This is the closest logged image to a view that we're going to just give the network to render. This is the novel view. You see we moved significantly closer to a bunch of vehicles on the side. And this is the surfal reconstruction that we have, texture surfals. And now this is the view of the world corrected again. And on the bottom, you have a similar setup. You move it slightly forward and reconstruct the view. You can do other things, such as a novel scene configuration. So the initial scene had the following objects in these configurations captured by our sensors. And this is our reconstruction. Now, you can perturb the object. So we moved out this vehicle back. And you can see that we get a somewhat reasonable, even though there's still some blurry artifacts reconstruction. And similar in this case, we rotated the vehicle and we get a reasonable reconstruction there. And so these are the kind of things you can do with the surfal one of the areas which I don't have time to get into is how do we measure that this type of realism is helpful. And for this, I refer you to the paper. We have some interesting evidence that, for example, detectors trained on the data that's the output of a full surfal GAN approximate better detectors trained with real data, and a few other metrics on novel view reconstruction that can be captured, say, with the second vehicle in the same scene and so on, that we get good results, showing that both parts of this setup are helpful over a vanilla solution. And so for that, I refer you to the paper. But again, another interesting example of things you can do with the type of data that we have in autonomous driving. There's some really fascinating areas of research and further improvement, not just along 2D and 3D box detection and tracking, but a lot of richer geometric reconstruction of the environments and trying to leverage that in interesting ways, right? And this concludes my talk. I hope I convinced you, and maybe some of you, that autonomous driving does offer some interesting problems of geometric processing. And also, please, if that's interesting, stay tuned and follow our research. We hope to have other interesting work to share in the near future. Thank you.